questions on anything at all? Yes, go ahead. Because the point that you're given there is a high point, and the high point on a sine graph occurs higher than 2 rather than 0. So that's why you want to set you the high point. So you need to figure out, making sure that high point is matching with the high point of the original graph. So that's why it's 0 in the second problem, because it was a high point of cosine. Yeah, so that's why you said that one. 0. And the first one was a little bit different. Yeah. Other questions at all? All right, well, let's go ahead and talk about a couple of these application problems that we didn't get a chance to get to last time before we get into the new stuff. So we spent the last couple of days of last week talking about inverse trig functions, did some properties of inverse trig functions, talked about domain restrictions, did some computational type problems with inverse functions. Talked a little bit about simplifying expressions that had inverse trig functions in them. But let's do a couple of applications on things that we might want to find. So, as far as angles go. So, pardon me, we've done applications where you've been given the angle and find a distance out of the triangle. But this one's going to give you pieces of a triangle and then asks you to figure out an angle. So, let's look at this first problem where they got a shuttle liftoff being filmed by a camera. It's 750 meters from a launch pad. The first angle, or the first part tells you that you're going to let theta be the angle of elevation, and s is the height of the shuttle. So if we draw a picture here, a triangle, let's assume that our triangle is a right triangle here. If this is our camera and this is the launch pad over here, what pieces can we label according to what we're given in the problem?
The distance between the camera and the launch pad.
Okay, and that's going to be 750. Good. So we can label that piece. What else can we label?
So is the height 1200?
So we'll do something when the height is 1200. Bless you. The letter they gave us to represent the height is what in this case? S. So I'll make that an S. And then what else? The theta is going to be where? Yeah, good. At the camera, good. Yep, the theta is going to be there because it told us that the angle of elevation is theta. So we'll have theta down here as our angle by the camera. We know that this distance between the camera and the launch pad does not change. It's always 750. And the S is the height of the shuttle at whatever time. Okay. So we've got our right triangle set up here. What trig function does it look like we're probably going to be involving here? Tangent, right? As a matter of fact, if we just use the tangent function, what expression can you set up that relates the theta and the s? Good, s over 750, right? The tangent of theta will be opposite over adjacent. Right? Now this isn't what the problem asked for. It's almost what the problem asked for, but it's not what the problem asked for part A. The problem says find theta as a function of s. What that means is that when you plug in an s, you're supposed to get out a theta, right? Meaning, I want theta equals something with s's in it, right? That's what it means to be as a function of s. It means that the theta is all by itself, okay? What do I need to do to that equation to put theta all by itself? And do the inverse tangent of both sides. That's exactly right. So rewriting this with inverse functions, this is what the problem is asking you for. My S's and my 5s look way too much alike. Whatever. So that was what the problem was actually asking for. We solved that for theta. So when you plug in an S, you're supposed to get an angle. I just need to do that one last step for that. Pardon me. One thing we should probably make sure that we're okay with, pardon me, is that our restrictions are okay, right? If I do inverse sine or inverse cosine, I need to make sure restrictions are okay. Is there anything that you cannot plug into the inverse tangent function? Or can we do the inverse tangent of whatever we want? So remember, domain of the inverse tangent is going to be the same as the range of the tangent function. What is the range of the tangent function? All real numbers, right? Because it goes up like this, and then it goes up like this, and up like this, right? Over and over again, right? So if the range of the tangent function is all real numbers, the domain of the inverse is all real numbers. So is there anything we cannot plug in for x? No, we're good. It's all real. Good. So there shouldn't be any issues there. The numbers that come out of this should be in between what? This is just more of a reminder of our inverse function. When you get an angle out of the inverse tangent, what is it always in between? Yeah, negative pi over 2 to pi over 2, right? It's always an angle in quadrant 1 or 4. Now, in the context of the problem, we always need to be having an angle that's in quadrant 1, the way we drew it, right? But what would you have to plug into what type of number would you have to plug into the inverse tangent function to get an angle out in quadrant 4? What kind of a number would you have to plug in to get an angle in quadrant 4? Negative. Is there ever going to be a negative value plugged in for S here? No, we didn't shoot the rocket into the ground, right? This is always going to be a positive height. So we're all good as far as all that goes. The problem didn't ask for that, but I just wanted to remind you things about the restrictions and the domains and the range and all those things that we talked about last week. All right, that was part A, by the way. That's all I asked for. Write theta in terms of S. Right? Theta is a function of S. Okay. All right, second part. If I want to find theta when S is 1,200 meters, what do we need to do? Yeah, just plug 1,200 in. So theta is inverse tangent of 1,200 over 750. Depending on the context of the problems, they may want degrees or they may want radians. Just make sure you have your calculator set in the correct mode for what it's asking for. Based on the second example here, it says degrees. So let's go ahead and do this in degrees. I will ask you this, though, before you type anything into your calculator. Since the number on the inside is bigger than 1, 1,200 is definitely better than 750. Will the angle you get out be less than or greater than 45? Greater than. The reason why I use 45 is because tangent of 45 is equal to what? 1. Yeah. So since that number is bigger than 1, I know I should be getting an angled out that's bigger than 45 degrees. What do we get? 57 point, would you say 994? Yeah. Okay. It's just little things like that that help you make sure that the answers you're getting make sense, right? I know tangent of 45 or tangent of pi over 4 is equal to 1, right? So if I'm putting a number bigger than 1 in the inverse tangent function, I should get an angle that's bigger than 45. And I did. Okay. If you would have got 12.8, probably type something in wrong somewhere along the way. This one okay? All right. Let's do the second one here. Pardon me. Got a sand pit that's 12 by 18. you're gonna take a rope, string it across diagonally, and it wants to know the angle the rope makes with the longer side. And then it asks how long is the rope. Well, if we've got a 12 by 18, do I need any trig to tell me what the length of the rope is? No, we use Pythagorean theorem, can't we? Okay. So that part's not really the interesting part. You can do Pythagorean theorem there and get the length of the rope. But let's ask about the angle the rope makes with the longer side. So which angle am I looking for the way I have drawn my picture here? Yeah, this one over here, right? Angle makes with the longer side. So usually I would just rather just write it in terms of the trig function that I know and then do what I need to do to get the answer. If I'm looking at theta and I have this 12 and this 18, what trig function is going to relate those sides nicely with theta? Tangent again, right? Tangent of theta is 12 over 18. So if I want to solve for theta, we need to do inverse tangent. Good. What do we got? A 3 that goes, 6 that goes into both. Inverse tangent of 2/3. Which gives you about what? 6/9, is that what you said? Does it make sense that it's less than 45? Yeah. That number is less than 1, so it should make that sense that it's less than 45. I'm not going to do the other part because I figure you can do Pythagorean theorem. That okay? I'll leave the last one for you for practice. Anyway, that's what we're going to use inverse trig functions for, is to help us solve equations like this. Right now, the equations are going to be pretty straightforward. Later on, we will need to use inverse trig functions to help us do more complicated trigonometric equations. We'll also do some inverse trig functions here in this next section when we start talking about solving triangles using what's referred to as the law of sines. Notice in those previous two examples that we did, and in that third example, if you go through that one yourself, you're going to use right triangles and all those things to help us figure things out. Well, not every triangle is a right triangle, right? So we need ways to help us solve triangles, figure out missing pieces of triangles. Remember, that's what solving a triangle means. Getting all the sides and all the angles. Okay, that's what solving a triangle means. We're going to need to figure out other ways to help us solve triangles. One of those ways is referred to as the law of sines. Next week we'll have another way referred to as the law of no sines. Okay? So this week's lecture is all about trying to get the law of sines down and figure out those pieces. So, just to set down some standard notation that we like to use for triangles, and we've talked about this a little bit. Mathematicians love their Greek letters. Okay? So, if I have a triangle, I'll just throw this off to the side. I'm just doing this to make sure that I'm setting down my notation. Okay? And I think we've talked about this a little bit before, but since we're not going to have a right angle as one of our angles, I want to make sure that we're all on the same page. Okay? If I look at this angle at A, it's made up of two sides. So in terms of A, it's hard to say which one is which based on what the letter A is. However, triangles only have three sides. right? What's called a triangle. Okay? So this opposite side never touches, or this side on the other side here never touches the edge. So when we talk about labeling sides, we always go with the one that's across from the letter that's in the triangle. Okay? So since I have my letter A here, capital A, I'll refer to this side as little a. And then likewise, since this is capital B here, I'll refer to this as little b. Since it's capital C here, we'll do little c. Okay? So that's our convention for labeling the sides. All right? Now let's talk about convention for labeling the angles. You could write angle A, angle like you did in geometry class, right? Use a little angle symbol, angle A, angle B, angle C. But mathematicians love their Greek letters. Okay? So what we'll do is we'll convert these, our alphabet letters into Greek letters. So the angle at A we'll refer to as alpha. The angle at B we'll refer to as beta. And the angle at C we'll refer to as gamma. The first three letters of the Greek alphabet, alpha, beta, gamma. Okay. So alpha will be the angle, and typically what we think about is the measure of the angle at A. Beta will be the measure of the angle at B, and so on and so on. Okay. All right. So going back to the picture here that I have where we're going to develop our law of sines, I'm going to go ahead and draw in my alpha here at A and my beta here at B. Yes, gamma is up there at C, but I've got a helping line in there that's going to connect pieces for us. So I'm going to label the C right now. All right. The whole point of this is that you're going to be given some information about a triangle, and you want to figure out the rest of the information. So right now, I've got 4 letters, A, B, alpha, and beta. Let's assume that we were given 3 of them and we wanted to figure out the 4th, and we need to figure out some way to figure out the 4th. Yeah, that's what our goal is here, right? Maybe I was given A, B, and beta, and I need to figure out alpha. Or I was given alpha, B, and A, and I need to figure out B. Okay? All right. That's our goal here. So we don't have right triangles, so I can't say anything in particular, but notice that I put a helping line in here. In this helping line, I did create a right triangle. Okay? So for as an intermediate step for the time being, let's label this H. I now see 2 right triangles. Using the left one, the one on the left, I see an alpha, I see a B, and I see an H. Do you see a trig function that relates those 3? I bet you can guess what that trig function is without even knowing what the triangle is, given the fact that the title of the section is Law of Sines. What trig function do they think you might want to use? Sine. Ooh, hey, I'm shocked. What do we have? Sine of alpha equals H over B. Good. Oops. Now look at the right triangle, the one on the right side. They're both right triangles, but look at the one on the right side. What trig function do you see that you can relate beta, H, and A? Sine again, right? Sine of beta equals H over B. Good. And I wrote B, or H over A, I'm sorry. We okay with those? Notice both equations have the same H in them. And remember, I said the whole point of doing this is because you were given alpha, beta, A, and B. I don't care about H. I want some relationship between alpha, A, beta, and B. Can you use those two equations and get rid of H? Get a different equation that doesn't involve H in it at all? I probably wouldn't ask the question if the answer wasn't yes, right? So let me ask it a different way. How can you put those two equations together to give me another equation that doesn't involve H at all? Go ahead. Yeah, exactly. We can do substitution, right? I can solve for H in one and plug it into the other. I'm going to do it slightly differently, but it's the same concept. Let's solve both of them for H and then put them together. Okay? So this one, we would have H equals B sine of alpha. This one would have H is A sine of beta. They're both equal to H, so let's set them equal to each other. Good. Yeah, exactly right. B sine alpha is A sine beta. You said it the other way around, but it's the same thing. Okay. That gives us an equation that involves A, alpha, B, and beta. So if you knew three of them, you could figure out the fourth. Right? We write this slightly differently. We put all the things related to A together, the angle at A together, the ones for the B together. So we would write this as sine alpha over A equals sine beta over B. Okay. Now, of course, we still have we have a third angle and a third side, right? But I labeled the picture A, B, C to start with, didn't I? If I relabel the letters, does it matter? No. I could have called this C and this gamma, and I would have had the exact same thing, wouldn't I? So I can actually set this equal to sine of gamma over C, and this is what's known as your law of sines. Those ratios all have to be the same in the triangle, no matter what triangle it is. So if you do the sine of the angle and over the opposite of the side opposite from it, right? The one that doesn't make up that angle, that has to have the same ratio as doing the exact same computation for the other two angles. So it's cool, right? It's a neat property. Let's see if we can put it to use. So in this first example, you are being asked to solve the triangle. In every problem that asks you to solve a triangle, you are going to be given three of the values, and you have to figure out the other three values. You'll be given three, you have to figure out the other three every single time. What solving a triangle means. Now, in application problems, typically you're asked to find one thing. It'll be the same problem. It's the same premise, I should say. All right, so let's look at this triangle. We're given two angles and a side, and an included side. Well, if I know from geometry, I know that if I have two angles, I know the third, because what do you have to do? Well, what do the angles have to add up to in a triangle? 180, right? So if I know two angles, I know the third. So if I know two angles and a side, I've completely determined the triangle. There's exactly one triangle that satisfies those properties. Okay? The reason why I'm saying that is because there's going to be some issues later on. Okay? But if I have two angles and a side, one triangle is all you get. Okay? All right. So let's do the easy one first. It doesn't require any trigonometry at all. If I want to figure out what gamma is, the angle at C, how would you figure out gamma? Yeah, add the other two and subtract it from 180, right? That'll be 180 minus the sum of the other two, right? Agree with that? 118 plus 22 is 140. Take that from 180, you get 40. Yep. Okay. All right, so figured out gamma. That was here. This side would be little a. This side over here would be little b. Why did I need to know what gamma was? Well, that's the angle across from 24, isn't it? Remember, in order to figure out, in order to be able to use the law of sines, I need to know three things and figure out the fourth. Well, at the very least, if I need to know three things, I have to know one of the angles, right? At least one of the angles, right? So I needed that 24, or that angle across from that. All right, so let's go over here. So let's say you wanted to figure out A first. What equation could you set up to get A? Yeah, go ahead. Good. That's law of sines, right? Now you can solve for A pretty easily, right? I hope it's pretty easily. It's not too hard of an algebra problem to do. Your A will be what? 24 sine of 118 divided by sine of 40. Again, this is important to make sure your calculator's in degree mode. All of these problems with solving triangles will ask you to do it in degrees. So make sure you're in degree mode for it. What do you get? It won't be degrees. It'll be the length of a side, right? Yeah. 32.96. Is that what others got? Okay. We also need to figure out B. We now know A. We could use the value of A to help us find B. However, if you do that, make sure you keep all of your digits in your calculator. Don't round it and then do it. If you round and then use that rounded length of the side to do the next side, it's going to compound rounding errors. I would suggest not doing that. I would always use the values you're given as much as you can. Only use previously calculated things if you have to. It's always best to be given those exact values that you're starting the problem with. So how would we figure out B using C again? What would you have? What would you set up to find B? Good. We're still going to use that sine of 40 over 24, but instead of looking at the A, let's look at the B. Same equation, just different things here, right? But the same way we set up the equation. Solve. Your B will be, what is that? 24 sine of 22 over sine of 40. And what do you get in that case? Is that what you said?
I said about.
Yeah. Okay. Is okay? The process okay? We're gonna do more examples. I'm not gonna say, oh, that's it, we're done. We should probably be happy, yay, we're done. See ya. All right, anyway, is this okay? Let's make sure the things make sense. Make sure the answers make sense. What should happen to your sides as your angles get bigger? What I mean by that is, should the side across from 22 be bigger than or smaller than the side across from 40? Should the side across from 22 be smaller than or bigger than the side across from 40? It should be smaller, right? That side across from 22 should be the smallest side of your triangle. The one across from 40 should be the next smallest. The one across from 118 should be your biggest. Is that what we got? Yeah. And that's the way it should work, right? The bigger the angle, the bigger the side across from it should be. So again, this is just, all I'm doing here is just trying to give you things to look at as you're doing the problems to make sure your answers make sense. Okay? You should always think about that when you're coming up with a problem answer, right? Make sure things make sense. All right. Work on the next one for a minute, and then we'll chat about it. Which value did you figure out first? Yeah, the alpha, right? It's probably the easiest thing to figure out, right? We might as well go ahead and get that done. So your alpha should be 180 minus the sum of the other two. We get 97, what, 83? Did I do that right? That okay? All right, so what did you set up next? Yeah, go ahead. Okay. Sine of which one? I'm sorry. Which angle did you use? I just didn't hear you. That 53. Thank you. I just didn't hear what you said with the angle. Sorry, I just didn't know which one you were looking at. So, okay, good. So, you need to figure out what the C value is. Doesn't really matter if you do it first or second, right? After that one. Okay. So sine of 44 over 7, you're given the 44 and the 7. I'd use that one for both parts because those are the ones that were given to you. So doing the sine of 53 over the C. A little bit of algebra now, right? You should have C equals 7 sine of 53 over sine of 44. And you get what? 8 exactly? Or 8.00? Is that what others got? 0.04? Okay. Does it make sense that it's bigger than 7? Well, why does it make sense that it's bigger? The angle's bigger, right? What equation did you set up for the other one?
Sine 44 over 7 equals sine 83 over 8.
Okay. Then again, you should have something very similar. Oops. As far as the equation to solve. 7 sine of 83 over sine of 44. And you get about what? 10.00. Okay, cool. Is that what others got? Is that okay? You're all very excited about it, I can tell. All right. So I mentioned a little bit ago that there might get little monkey wrenches thrown in every once in a while. Notice in the previous two problems that we did, we were given 2 angles and a side. Well, again, if you know 2 angles, you know the third one, right? For a fact. Okay? Which means you really, if you're given 2 angles and a side, you're really given 2 angles and an included side, which is one of your congruence theorems for triangles in geometry, right? There are 4 of them that you should have talked about in the geometry class. They're typically labeled as SSS, SAS, ASA, and AAS. Okay? And they're just talking about for what information you're given. So the first one we refer to as side, side, side. What that means is that you're given all 3 sides of the triangle. So, thinking about it another way, if I tell you that the sides of a triangle are 3, 4, and 6, you know exactly what that triangle is. You can't change the angles. Okay? If you have a triangle that's 3, 4, and 6 for the 3 sides, there is exactly one triangle that has that. That's what side, side, side means. Okay? The other ones, the SAS is side angle side. Now it's written that way on purpose. It says side angle side, so you're given 2 sides and an included angle. the angle that you're given has to be in between the two sides. The two sides that you're given, the angle is the one that's made up by those two sides. That's what it means with the included angle. Okay. So if you're given that you've got sides of 7 and 9, and the angle between them is 37, then you know exactly what the triangle is, what this theorem says. Now, notice that either of these two things is going to be really, really hard to solve with law of sines, right? Because law of sines has sine of alpha over A, sine of beta over B. I've got to know at least one angle, right? So I can't use law of sines for side, side, side. Sine angle side is also hard with law of sines. Because if I have side 1 and side 2 and this angle, well, if I have this angle, I need to know what this opposite side is, or I need to know what this angle is, right, to be able to use law of sines, right? So neither of these are good for law of sines. These two are going to be the law of cosines, which we'll talk about next week, okay? Those two require law of cosines, and we'll talk about how we do those next week, okay? The other ones, notice that we have angle side angle. Oops. This is given two angles and the side between them, or the side included. This is angle side. This is given two angles and another side. Really, these two are the same, because if you're given two angles, you know the third. So if you're given two angles, you can always do angle side angle, right? Notice that these two congruence theorems are illustrated in the previous two examples that we did. The first example is an example of angle side angle. The second example was another of angle side. We go back to the example we just did. That's how I set them up. Right? Another. Yeah, that's an O. That's a goofy looking O. It's the pen just didn't grab the rest of it. Sorry. So the last two are our law of sines that we want to use. And in those cases, we always, assuming the problem is set up correctly, we always get exactly one triangle. So the end of this discussion, and we'll do some more examples here, is what's not a congruence theorem. All right, so here's the picture. Suppose that I'm given alpha, and I know the opposite side A. And I'm given side B, but I'm not given any other angles. Well, notice I've drawn two more pictures, or drawn two more sides, two possibilities here, right? My side A might come from C this way and intersect this side down here, or it might come down from C this way and intersect this side down here. If I got a pivot point there and hit both sides, right? If you think of C as being fixed as a center, I could think about this just rotating around and hitting this side again. I've got two possibilities, maybe. Okay. Notice in this case, I would be given two sides and an angle that's not in between them. That might be better known as angle side. What would the abbreviation for that be? If I did angle side. Gets a few smirks, right? Yeah, that's not a theorem because it's ass. Okay? It doesn't work. All right? If you have two sides and an angle that's not included, it's not a theorem. Right? Okay? So there's three different possibilities. You might get exactly one triangle. It's possible that this side was long enough here that if you think about rotating it, you'd end up on the other side. You might get no triangle. This side might be not long enough. And it might just swing around up here and not intersect this side. Or you might get two. So this is what's known as the angle, the ambiguous case. So again, angle side side is not a congruence theorem. We might get 0, 1, or 2 triangles. Again, this is what's known as the ambiguous case. Okay. So hopefully I've got one set up here that's ambiguous right away, because otherwise this is going to be a really bad example to do. It's the first one. Pardon me. Okay. So let's set it up. I'll set up a picture just to start with. You may not have to draw the picture if you don't want to, but I like to draw the picture to start, even if it's not to scale. 25, 26, 70. Let's say I want to figure out this beta. What equation would you set up to solve for beta? Good. Just using the law of sines again, I can figure out that equation, right? And this equation is correct no matter if we have zero, well, we have no triangles and there's no solution. But this equation is correct whether we have 0 triangles, 1 triangle, or 2 triangles. Doesn't matter. Okay? If I want to solve for beta now, I would need to multiply by 26 and then do the inverse sign, right? We agree? Goodness gracious. So if I do all of that at once, I would have 26 sine of 70 over 25 and then take the inverse sign, right? That's what we would get. What do you get for that? 77.76. Well, let's think about this for a second, and then we'll probably finish it up next time because I got about 2 minutes. Pardon me. Remember when you did inverse sine, it always gives you an angle in quadrant 1 or 4. Everything here is going to be positive, so you're always going to get an angle in quadrant 1. However, there's also an angle over in quadrant 2 that has the exact same sine value, right? Always. There's always one in quadrant 2 that has the exact same sine value, right? It's the supplement. It's 180 degrees minus that angle. We'll always give you the same sign, okay? So what we always have to do, anytime we use the law of sines to find an angle, we always need to check if there's a second triangle. Here's how you check. Before you do anything else, I would always check. Is there a second triangle? Here's how you check. Oops. Find the supplement first. What would we get here? 102.24-ish, roughly. If I did that subtraction correctly. Add the angle you're given, which was 70, right? We get 172.24-ish. Yeah. Is that okay? Can 2 angles in a triangle add up to 172? Sure. it's less than 180, right? As long as this sum is less than 180, there's a second triangle. We found the other one, okay? So working with this being an angle, figure out the missing angle inside. Working as this is an angle, the 102.24, find the other missing angle inside. We'll finish this up on Wednesday. We'll see more examples of ambiguous cases. Okay? And then we'll probably do some application problems as well. But this is how you always check to see if there's a second triangle. Okay? And I'll emphasize this again next time. So have a good one. We'll see you on Wednesday, if not before.